Welcome to part 2 of this series. Today we're going to create a simple Spring application. We will package it into a container image, then we will use GitHub Actions to automatically deploy a new version of the application to our Kubernetes cluster when new commits are pushed to the master branch. Let's start with the Spring Initializer website to create our Spring project. We'll add one dependency, the web dependency. Give your artifact a name, then click Generate to download the zip file. Extract the zip file and open the project in IntelliJ. We will keep the Spring app very simple. We'll add two endpoints, one for health and one to return the app version. So let's create the health controller class. Add the REST controller and the request mapping annotations. Specify API/health for the request mapping. Next, we define a get mapping which will return a string. This will be used by Kubernetes for the health and liveness probes. Next, define a new get mapping for the version endpoint. This will return the app version, which we will read from our application properties. So define the version variable, and it will get its value from application version variable. Next, we need to define the variable in application.properties. In application.properties, define application_version, and the value will be taken from build properties, project.version. When we run our build, the value here will be replaced with the value from our pom.xml. In order for variables to be replaced in our resource files, we need to tell our build to do so. Open the pom.xml file and under build, add the resources tag, then resource. Then specify our resources directory and set filtering to true. What this means is that when any of the resource files reference the build properties using the special syntax, they will be replaced with the actual values. Now let's run the app and test our endpoints. Let's check the health endpoint. And it returns the OK string. Next we check the version endpoint and we get back the version defined in pom.xml. Great. Next we need to define the building of our container image. We'll leverage the Spring Boot Maven plugin to do that. In pom.xml, scroll down to the plugins section and in the Spring Boot Maven plugin, add the configuration tag. Add the image tag and then we define the image name which we get from the docker.image.name property. We'll define this property later. Next, we need to define a couple of environment variables for the image builder to reduce the memory required to run the Spring app. First, we'll instruct the image builder to use the same Java version used by our project. Define the bp_jvm_version property and set the value to java.version from our properties. For memory, by default, the image builder produces a container image that requires at least 1 GB of RAM, but will reduce it to 256 MB. There's a handy little guide showing what properties need to be set for different memory profiles, and I'll include the link in the description. The first property for memory we need to set is the thread count. Define the bpl_jvm_thread_count property and set the value to 62. Next, we'll add additional Java tool options used by the app, so define the bpe append Java tool options, and we set the stack size to 256K. And reserved code cache size to 60 MB. And in order for these Java options to be added correctly, we need to add another property called bpe delim Java tool options. We set the space to preserve and the value is a single space. So that's our memory options configured. We want the image builder to push the container image to the registry after it's built, so set the image publish property to true. And since our registry uses authentication, we need to tell the image builder which credentials to use. After the image tag, define the Docker tag. Then publish registry and set the username property which comes from docker.registry.username property that we'll define later. And the password property that comes from the docker.registry.password property that again we'll define shortly. And that's our image builder configured. Now let's define all those properties we referenced. Scroll to the top to the properties tag. First, we define the docker.image.registry property, which points to our Digitalocean space we created. And I want the images to be stored under registry. Next, we define the docker.image.name property that is referenced by the builder. The image name consists of the registry plus image name plus tag given to the image. So the first part of the image name is the value from docker.image.registry. Then we add a slash and specify the image name, which we take from the artifact ID property. Then add a colon and specify the image tag, which we take from the project version property. And lastly, we need to define the Docker registry username and password properties. The values here will be passed in on the command line when running the build, as we don't want to store sensitive information in source control. So the username will come from Docker registry username command line property, and the password will come from Docker registry password command line property. So let's try and see if image building and pushing works. Open up a terminal and run the build image command, skipping the tests and passing our registry credentials. If you don't have MVN installed locally like me, we can use the MVN wrapper to run the MVN commands. And it seems there is a problem with registry credentials. Looking at our pom.xml file under publish registry, the username should come from docker.registry.username property. Now rerun the build image command, and in my case I don't have Docker running, so make sure to start Docker before running this command. Once that's done, we can see our app image is built and pushed to our private container registry running inside the Kubernetes cluster. Okay, great, that's our image building and pushing done. In order to run the app in Kubernetes, we need to define the Kubernetes resources. First, we'll create a Kubernetes deployment. In the resources folder, create a folder named Kubernetes. And inside, create a file called deployment.yml. Here, I suggest copying the contents from the GitHub project instead of typing it all out. What will happen is we will run our build, all the necessary variables will be replaced with values at build time, then we will take the produced YML files and push them to our GitOps repo, from which Argo CD will deploy any new updates. Let's go over the values here. The Kubernetes resource type is a deployment. The name and namespace of the deployment will be populated from the project artifact ID. For the spec, we define a replica count of 1, meaning this deployment will run 1 pod for our application. We set a revision history limit of 2, which means if we ever want to revert the deployment to a previous app version, we can go back 2 versions. Next, we define some boilerplate Kubernetes labels. Down in the spec, we define the image pull secret to use for authentication to pull images from our private container registry. Under containers, we define one container, and the image is populated from the docker.image.name property from our pom.xml file. The image policy is set to always, which means to always pull a new image from the registry. We give our container a name and define the 8080 port. Then we define the readiness probe, which lets Kubernetes know when our app has started and is ready to receive traffic. The readiness probe will wait 10 seconds before issuing the first probe. Then we have the liveness probe, which Kubernetes uses to know if our app is still working and not stuck for whatever reason. And lastly, we define some resource limits. We specify this app needs at least 64 megabytes of memory to start up, and we set a maximum usage of 256 megabytes of memory. Next, we need to define a service through which our app can be reached by other Kubernetes resources. Create a file named service.yml in the Kubernetes folder. And again, copy the contents from GitHub. Here we define the name and namespace of the service, which is populated with values from the pom.xml file. We set the port of the service to 8080 and the target port, which is the port our app is running on, which is also 8080. And the traffic will be routed to pods with the set selector, which matches the value from the deployment YML file. In order to receive network traffic from outside the cluster, we need to define an ingress. Create a file named ingress.yml in the Kubernetes folder. As usual, we define the name and namespace of the ingress with values from our pom.xml file. Next, we define the cluster issuer to use when generating SSL certificates. We set the ingress class to nginx, and we force SSL redirect to true, so that if our app is accessed via HTTP, the request will automatically be redirected to HTTPS. For the rules, we define the host with the value from server.host, which we don't have defined yet, but we will do so shortly. We set the path to root, and the traffic will be directed to our app service on port 8080. Lastly, for the TLS section, we define the host for which the SSL cert will be generated and the secret where the generated cert will be stored. Now for the server.host property, open up the pom.xml file and add the server.host property, and value here will be the domain to use for the Spring app. So decide on a hostname to use, set the value here, and ensure you add a DNS record for this hostname that points to the cluster load balancer. I will do that for my hostname right now. I will add a CNAME record for app1 that points to the load balancer domain, and add another record using the www prefix. Alright, our Kubernetes files are set up. Let's run mvn install and check the generated Kubernetes files. Next, we will work on the GitHub Actions. First, we need to have a repo in GitHub. So create a repo and push the project files to GitHub. We also need to create the GitHub repo and push a sample test file to it. It doesn't matter the file or its contents, since it will get replaced once we set up GitHub Actions. In the root folder of the project, create a folder named .github. Then another folder called workflows. Here, create a file called maven.yml. First, we give the workflow a name. Then we configure when the workflow should run, and in our case, we want it to run on pushes to the main branch. Then we define the jobs. We'll have one called build image, and it will run on Ubuntu latest image. Then we have the steps to execute in this job. First, we need to check out the code, so we write users actions /checkout at v3. That's the first step. In the second step, we need to set up the JDK to compile the code. Give this step a name, and we'll use another GitHub action here to set up Java. Lastly, we tell it which Java version we want to use. The third step will be to build the code and run tests. Give this step a name, then we want to run a command, mvn-b install. The fourth step will be to build and push the Docker image. Give this step a name, and we want to run the build image command. We also want to skip running the tests this time, since they already ran as part of the mvn install. Lastly, we need to pass the Docker registry username and password build properties, which are retrieved from the GitHub Actions secrets. The last step in our job will be to push the new Kubernetes deployment files to the GitOps repo. Give this step a name. We'll use another GitHub action here to push code to another repo. We need to give it an environment variable to use for pushing to the repo. Specify the API token GitHub variable, which gets its value from another secret called token. We'll add the actual secret in GitHub shortly. Lastly, we need to configure the GitHub action. Specify the source directory that will be pushed to the GitOps repo. In our case, the build Kubernetes deployment files are located in target classes Kubernetes. Next, we need to specify the destination GitHub username, then destination GitHub repo name. Next, set the user email. This will be used as the user for the commit added to the GitOps repo. Next, specify the branch we will be pushing to. And before we can finish off here, we need to create a GitHub token. Head over to GitHub, then Settings, then Developer Settings. Under Personal Access Tokens, click Find Grained Tokens. Click Generate New Token, give it a name, choose an expiration time. I'll choose 90 days here. For repository access, we will give this token permission for the GitOps repo only. For the repository permissions under Contents, select Read Only Access. then click Generate Token and copy the value. Now head over to the source code repo and click Settings, Secrets and Variables, and then Actions. Click New Repository Secret. For the name, set token and paste the value of the token and click Add Secret. Now do the same for the Docker credentials. Add new secret, set name to Docker registry username and set the actual username. Now again for the password, set name to Docker registry password and set the password and click Add. Now we will push our code changes and we should see GitHub Actions getting kicked off. So we can see the image was built and pushed, but there was a problem pushing the Kubernetes deployment files to the GitOps repo. And it looks to be a permission problem due to the 403 error. We need to go and edit the access token and add the read and write permission for the repo contents. With that done, we can go back to our GitHub action and rerun it. And this time everything completes successfully. And if we navigate to the GitOps repo, we can see the build Kubernetes deployment files are there. Alright, great. Now on to setting up Argo CD for continuous deployment. Now head over to Argo CD and log in with the admin account. First we'll connect our GitOps repo. Since it's a private repo, we need to add it with credentials. Go to Settings, Repositories, and Connect Repo. For method, choose HTTPS, then type git. Project as default. Now we need to get the repo URL. Head over to GitHub to the GitOps repo and copy the HTTPS URL and paste it there. Now we need to create the access token to enable Argo CD to monitor this repo. So head over to GitHub, Settings, Developer Settings, fine-grained access token, generate new, choose the GitOps repo and choose read contents and create the token and then copy the token. Since we set a password, we also need to provide a username. I think it doesn't matter what value you use here, but I just use my GitHub username. Then click connect and you should see a successful connection. Before we create the app to pull the deployment files, we need to create a Kubernetes secret to enable Kubernetes to pull our app image files from the private registry. And actually, before creating the secret, we need to first create the namespace for our app. So use kubectl to create the app1 namespace. And now you can create a Docker registry secret in the app1 namespace. Now we can go back to Argo CD and create the application. Give your app a name like app1. For project, choose default. Set the sync policy to automatic. This means when the config files change in the GitOps repo, it will automatically update the Kubernetes deployment in the cluster. Then tick auto create namespace just in case. For repo URL, choose the repo we added to Argo CD earlier. For revision, choose the master branch, and for path we write a dot, meaning use the YML files in the root folder of the project. For destination cluster URL, choose the default service and set the namespace to app1 and click create. And our Argo CD app is created. You can see it is in the process of syncing the deployment files. And if we navigate to the app itself, we can see all the resources created by it and the progress of deployment. You can also open up the pod and navigate to the log tab to see the app logs. Once the deployment is updated and the new pods are healthy, the sync process transitions to a synced and healthy state. Now let's use curl to check if we can reach our public app APIs. First, let's query the health endpoint. And we need to instruct curl to follow redirects using the L flag. And now we get back a response. Now query the version endpoint and we get back our app version. Next, what we'll do is test the workflow end to end. So we'll pretend we made some code changes to the app, like adding new features, and then we increment the app version. I will use the watch command in terminal to query the version endpoint periodically to see the version of the app being updated as the Kubernetes deployment is updated. So commit the change and push to GitHub. Now start the watch command to query the version endpoint and we get back the initial app version. I'll open GitHub Actions to see its progress. Now you can see the new deployment files have been pushed to the GitOps repo. Now Argo CD will realize the deployment config has changed. This may take a couple of minutes. You can also press refresh to force it to update, but I will just let it play out. So after a couple of minutes, Argo CD realized there are changes and it attempts to update the deployment. It will start the new version of the app in a new pod, and once the new pod starts up without errors, network traffic is directed to the new pod and the old pod is removed. And we can confirm that from the output of the watch command. We now get back the new app version. So well done for getting this far. Now you have a fully automated continuous deployment pipeline. Thank you for watching and see you in the next one.